Hello, friend. Welcome to Science for Sleep. Whether you are returning tonight or discovering this quiet corner for the first time, this is a gentle place to slow down, learn something soft and real, and let the day gradually fall away. Tonight, we are going to spend time with wood. Not just wood as a table or a chair or a floorboard beneath your feet, but wood as one of the strangest materials Earth has ever made. At first, wood can seem almost too ordinary to notice. It may be in the frame of a door. It may be in the pencil resting on a desk. It may be in the handle of an old tool, the beam of a house, the smooth back of a guitar, or the quiet shelf holding books in the corner of a room. But every piece of wood began as living tissue. It was once part of a tree that stood outside in wind, rain, sunlight, cold nights, and warm seasons. And one of the most surprising things about wood is that much of it was once invisible. A tree builds wood by taking carbon dioxide from the air. Carbon dioxide is a gas, too thin and clear for your eyes to see. Through photosynthesis, the tree uses sunlight, water, and that invisible gas to make sugar. Then it slowly turns that sugar into the hard walls of plant cells. So in a very real way, a wooden table is not only something from the ground, it is also something from the sky. If you enjoy these quiet journeys, you're welcome to subscribe. And if it feels natural, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. The quiet continues here, just as it is. Wood is not an element, even though people sometimes speak about it that way. An element is something like carbon, oxygen, iron, gold, or hydrogen. Wood is different. Wood is a biological material. It is made by life. Most dry wood is built from three main substances. One is cellulose, which forms strong fibers inside plant cell walls. Cellulose is also what makes cotton strong, and it is one reason a sheet of paper can bend without falling apart. Another is hemicellulose, which helps bind the fibers together. And then there is lignin. Lignin is darker, tougher, and more complex. It acts almost like a natural glue and stiffener, helping wood become firm enough to hold a tree upright. Without lignin, the world would not have forests in the same way. Plants could still be green and alive, but they would struggle to rise into tall trunks, thick branches, and high canopies. That is part of what makes wood so easy to overlook and so strange once you pause to notice it. Rock can form on dead worlds. Ice can gather on moons, comets, and distant planets. Metal can be forged inside stars and scattered through space after explosions. But natural wood requires far more than chemistry. It needs a world with light. It needs liquid water. It needs an atmosphere with carbon dioxide. It needs land where plants can grow upward. It needs roots, soil, minerals, fungi, seasons, and long chains of life passing from one generation to another. Even if life exists somewhere else in the universe, it may not grow trees. And even if it grows plants, those plants may not make anything like wood. So the board in a floor, or the beam above a ceiling, or the old wooden spoon in a kitchen drawer may be part of something incredibly rare. It is common here only because Earth is generous with forests. A piece of wood can feel simple in the hand. It can be warm, grainy, smooth, rough, pale, dark, heavy, or light. But inside, it is a quiet record of sunlight turned solid, air turned into structure, water lifted from the soil, carbon stored in rings and fibers, a living planet shaping itself into something strong enough to hold weight, burn with warmth, float on water, and last for centuries when cared for. And that is where the story of wood really begins. Not in a lumber yard, not in a workshop, not even in a forest, but inside a living tree, quietly solving the problem of how to stand tall against gravity. Inside a living tree, wood begins with a simple pressure from the world around it. A tree has to lift its leaves into sunlight. The leaves are the green surfaces where photosynthesis happens, where carbon dioxide from the air and water from the soil are turned into sugar. That sugar feeds the tree and helps build new tissue. For a tiny seedling, this problem is small. A young maple sprout may only need to rise a few inches above the leaf litter. Its first stem can be soft, green, and flexible. It bends easily because it is still mostly tender plant tissue filled with water. But a tree is trying to do something much larger. It is trying to keep growing upward while its roots stay buried in darkness. The roots pull water and minerals from the soil. The leaves need open air and light. Between those two worlds, the trunk has to become strong enough to hold the tree together. Wood is the answer to that slow upward pull. It gives a tree a firm body. It lets the trunk resist wind. It lets branches spread outward without collapsing under their own weight. In a forest, this becomes a quiet contest for light. A sugar maple may grow towards small openings in the canopy. A white pine may rise straighter, sending its needles above nearby shrubs and younger trees. A coast redwood in California can grow more than 300 feet tall, lifting its crown into fog and sunlight high above the forest floor. At that height, gravity is no small detail. Every branch has weight. Every wet leaf holds water after rain. Every gust of wind pushes against the tree like a slow, invisible hand. The trunk needs stiffness, and that stiffness comes from millions upon millions of wood cells packed together in long vertical lines. Many of those cells are stretched in the same direction as the trunk. This gives wood its grain. A board splits more easily along the grain because the fibers already run that way. Across the grain, the structure resists differently. This is why a straight wooden pole can be light enough to lift, while still strong enough to hold a roof, a fence, or a bridge rail. A soft green plant stem usually grows for one season, or a short part of a season. It may flower, make seeds, and fade back. A woody stem follows a different rhythm. Just under the bark is a thin living layer called the cambium. The cambium is delicate, even though it helps make the hard material we recognize as wood. Each growing season, this layer produces new cells. Some become inner bark. Many become new wood. Over years, those new layers gather around the older ones. The tree does not have to replace its whole trunk each spring. It builds outward from what is already there. That is why a cut log can show rings. Each ring is part of a long record of growth. In temperate places, where winters slow growth and spring begins it again. One ring often marks 1 year. A young oak might add a thin new layer each season. An old bristlecone pine in the White Mountains of California can keep adding wood for thousands of years, even in dry, rocky soil, where the wind is cold and the growing season is short. Some living bristlecone pines are more than 4,000 years old. Their trunks may look twisted and weathered, with dead wood exposed beside narrow strips of living bark. Yet the living parts can keep adding new wood, season after season, with great patience. This is one of wood's quiet strengths. It allows a tree to carry its past while still growing. The older wood inside the trunk becomes part of the support. The newer wood near the outside takes on fresh work. In many trees, the central wood becomes hardwood, darker and often filled with protective chemicals. Hardwood no longer carries water, but it helps the trunk stay firm. Around it lies younger sapwood, paler and more active. Together, these layers let a tree become both old and upright. A tree is rooted in one place, yet its body is always answering force. The pull of gravity, the push of wind, the weight of branches, the need for leaves to reach light above the shaded ground. Wood makes that possible with a structure that grows slowly and stays behind. And once the trunk can stand, a quieter mystery remains inside it. This hard material also has to help lift water from the roots toward leaves moving gently in the air. That same hard trunk, holding the crown of the tree in the air, is also filled with old pathways for water. Inside most of the wood is a tissue called xylem. Xylem is the part of a plant that carries water and dissolved minerals upward from the roots. The word may sound technical, but the idea is simple. A tree needs a way to move water from dark soil to sunlit leaves. Roots take in water through tiny root hairs, which are fine thread-like growths near the tips of young roots. Those root hairs touch small spaces between soil grains, where water gathers around bits of sand, clay, and decaying leaves. Mixed into that water are minerals such as nitrogen, potassium, calcium, and magnesium. These minerals help the tree make new cells, keep leaves working, and repair small injuries. After water enters the roots, it begins a long, quiet climb. In a maple, it may travel a few dozen feet. In a mature eastern white pine, it may rise more than 100 feet. In the tallest coast redwoods of Northern California, water can move over 300 feet from root to crown, reaching needles that sit higher than a 30-story building. There is no little pump hidden inside the trunk. A tree lifts water through physics that happens slowly and constantly. The leaves release water vapor through tiny openings called stomata. A stoma is a small pore on the surface of a leaf. When these pores open, carbon dioxide enters so the leaf can make sugar, and some water escapes into the air. As water evaporates from the leaves, it creates a pull on the water behind it. That pull travels downward through the narrow xylem tubes, drawing more water upward from the roots. This works because water molecules cling to each other. That cling is called cohesion. Water molecules also cling to the walls of the tiny tubes, which is called adhesion. Together, these forces help create one long, delicate chain of water inside the tree. The chain is thin, quiet, and under tension, like a stretched thread. A break in that chain can create an air bubble, and the bubble can block movement. Trees have different ways to reduce this risk. Some grow many narrow pathways instead of fewer wide ones. Some produce new xylem each year, so fresh channels can keep water moving even when older ones become blocked. In conifers such as pines and spruces, much of the water travels through long, narrow cells called tracheids. They are tapered at the ends and connected by tiny openings. In many flowering trees, such as oaks and maples, water often moves through wider vessel elements. These vessel elements line up end to end, forming tubes that can move water more quickly. That difference is one reason oak grain can show large visible pores, while pine often has a smoother, more even look. A cut board still carries the memory of this plumbing. The lines, pores, and grain patterns in lumber are traces of cells that once helped a living tree drink from the ground. When a carpenter looks at oak, ash, or walnut, the pattern is partly a record of how water once moved. Ring porous woods, such as white oak, form larger vessels early in the growing season. Diffuse porous woods, such as maple and birch, spread smaller vessels more evenly through the year's growth. These details change the way wood looks, bends, dries, and takes stain. They also remind us that wood is never just a plain solid. Under a microscope, it looks closer to a bundle of tiny straws, walls, chambers, and passages. Some spaces are wide enough to see as pores. Others are far too small for the eye alone. A single piece of wood may contain millions of cells arranged in careful directions. During the life of the tree, some of those cells carried water. Others stored food. Others helped support the trunk as it grew heavier with each season. This is why a tree can seem still from the outside while so much movement is taking place within it. On a calm morning, when the leaves barely move, water is still rising. Sunlight warms the crown. Moisture leaves through the stomata. Roots keep drawing from the soil. The trunk stands quietly between those two worlds, holding the tree upright while guiding water upward through channels thinner than hair. And when wood is viewed this closely, the material becomes stranger again. Its strength comes from walls built at the scale of cells, and those walls are made from fibers and natural binders arranged with remarkable care. At the scale of a human hand, wood can feel solid and simple. Under a microscope, it becomes a carefully built material full of walls, fibers, and tiny spaces. Each wooden surface began as plant cells packed together inside a growing trunk. Those cells had outer walls, and the strongest part of wood comes from the way those walls were built. The first major ingredient is cellulose. Cellulose is made from long chains of glucose, which is a simple sugar. A tree makes that sugar in its leaves using sunlight, water, and carbon dioxide from the air. Then the tree links many sugar units together into long strands. Those strands gather into thin bundles called microfibrils. A microfibril is like a very small cable inside the wall of a plant cell. It is far too tiny to see without powerful tools. Yet billions of these little cables help give wood its strength. Cotton is mostly cellulose too, which is why a cotton thread can be thin and still hold together. Paper also depends on cellulose fibers pressed into flat sheets. In wood, the fibers are arranged in thicker, stronger walls that can hold a tree upright for many years. Cellulose is especially good at resisting pulling forces. When a branch bends in the wind, some of the wood fibers are being stretched. The long cellulose chains help keep those fibers from tearing apart too easily. Around those cellulose bundles is another substance called hemicellulose. Hemicellulose is made from shorter, more branched sugar chains. It does not form the same long cables as cellulose. Its job is more like a flexible connector. It helps hold the cellulose bundles in place and links them into a wider cell wall structure. A useful comparison is a woven mat. The long fibers give the mat direction and strength. The smaller connecting material helps keep the weave from falling loose. In a living tree, this mix has to be strong enough to resist gravity, while still flexible enough to move slightly in wind. A completely brittle trunk would crack too often. A completely soft trunk would sag under its own weight. Wood finds a calm middle place between those extremes through the way its cell walls are arranged. Then comes lignin, one of the most important substances in the history of plants. Lignin is a complex material that fills spaces inside the cell wall. It stiffens the wall and helps protect it from water, crushing, and decay. In many kinds of dry wood, lignin makes up roughly 1/5 to 1/3 of the material by weight. Softwoods, such as pine and spruce, usually contain a little more lignin than many hardwoods, such as maple or birch. That extra lignin helps explain why conifer wood often behaves differently when cut, pulped, burned, or broken down by fungi. Lignin also gives wood some of its color. Freshly cut pale wood may darken as oxygen and light slowly change its surface chemistry. In darker heartwoods, such as walnut or mahogany, other natural chemicals gather as the tree ages, adding deeper browns, reds, or purples. The cell wall is where all of this becomes practical. A tree is building with small parts, yet the result can be enormous. A coast redwood can rise higher than the Statue of Liberty. A white oak can grow a trunk wide enough that two people can barely reach around it. A spruce can produce straight, light wood, used for framing houses, musical instruments, and long, narrow boards. The same basic materials appear again and again, arranged in different patterns. Cellulose gives tension strength. Hemicellulose helps bind the structure. Lignin adds stiffness and resistance. Together, they create a natural composite, which means a material made from different parts that work better together than they would alone. Fiberglass is a human-made composite, with glass fibers held in resin. Concrete with steel reinforcing bars is another example. Wood arrived at its own version through growth. It forms quietly under bark, one layer at a time, using sunlight as the energy source and air as part of the raw material. This is why wood can be carved with a knife, split with an axe, bent with steam, polished smooth, or shaped into beams that hold thousands of pounds. Its strength comes from small walls repeated countless times. Its lightness comes from hollow cells and open spaces. Its flexibility comes from fibers that can give slightly before they fail. Seen this closely, wood becomes less like a simple solid and more like a living design left behind by growth. And among all its ingredients, lignin carries the deepest consequence. Once plants could make enough of it, life on land began reaching upward in a new way. Lignin changed what plants could become. Once this tough material appeared inside plant cell walls, the green life on land gained a new kind of strength. A small moss can live close to damp ground. Its body stays low, soft, and thin, because water and nutrients only need to move short distances. A tall tree faces a much harder task. Its leaves may be far above the soil. Its branches may spread in heavy layers. Its trunk has to hold firm through rain, snow, dry weather, and wind that keeps pressing against it year after year. Lignin helped solve that problem. It made plant cell walls stiffer. It helped them resist crushing. It also made the walls more resistant to water passing through too freely, which mattered because land plants had to control where water moved. In early plant life, water was a constant challenge. The first land plants came from ancestors that lived in water, where their tissues did not need to support much weight. Water itself helped hold them up. On land, gravity became more demanding. Air surrounded the plant instead of water. Sunlight was abundant above the ground, but reaching it required height. By around 420 million years ago, during the Silurian period, small vascular plants were spreading across parts of Earth. Vascular means they had internal tissues for moving water and nutrients. These early plants were still small compared with modern trees. Many stood only a few inches or a few feet high. Their simple stems rose from wet ground, often near streams, muddy flats, and damp lowlands. Then wood-like tissues became more important. By the Devonian period, beginning about 419 million years ago, plants were becoming larger and more complex. Some developed stronger stems, some grew branches, some formed deeper roots that entered soil instead of only resting near the surface. Lignin was one of the materials that made this shift possible. It strengthened the xylem, the water-carrying tissue inside stems. That mattered because xylem had to do two jobs at once. It had to move water upward. It also had to keep the plant from folding under its own weight. A tube that carries water through a tall plant has to stay open. If the tube collapses, water cannot rise. Lignin helped keep those tiny tubes firm, like reinforced walls around a narrow passage. The change can be pictured slowly. A low green landscape begins to gain height. Slender stems rise higher. Roots reach deeper. The ground becomes shaded in places where older land may have been open to direct sun. By about 385 million years ago, forests of Archaeopteris were growing in parts of what is now North America and Europe. Archaeopteris was one of the most important tree-like plants of the Devonian world. It had woody trunks, branches, and leaves that looked somewhat fern-like. Some individuals may have reached more than 60 feet tall. For that ancient time, this was enormous. A living structure could now lift a crown high above the ground and hold it there. The arrival of forest changed more than plant height. Roots broke into rock and helped form deeper soils. Fallen leaves and dead wood added organic matter to the ground. Shade created cooler, wetter spaces where smaller plants and early land animals could live. Forests also affected the air. As trees grew, they pulled carbon dioxide from the atmosphere and stored carbon in wood, roots, and buried plant matter. Over long stretches of time, this helped change Earth's climate. Wood was becoming part of the planet's larger breathing pattern. The land itself began to look different. Streams moved through root-bound banks. Soils held more water. New habitats appeared beneath branches and between trunks. A tree was still an individual living thing, but forests acted on a much larger scale. They shaped air, soil, water, and light across whole landscapes. Lignin made plant walls tougher, yet its greatest effect was seen in the quiet spread of forests. A chemical inside cell walls helped create shade across continents. It helped plants rise from damp ground into the open air. It gave Earth trunks, branches, canopies, and fallen logs. Once wood appeared at scale, the story of the planet began to widen. The material inside a single trunk became a force that could change the surface of Earth itself. Across the ancient land, wood began changing the shape of the world. During the Devonian period, between about 419 million and 359 million years ago, Earth's continents looked very different from today. Large animals had not yet walked through forests. Flowering trees had not appeared. There were no oaks dropping acorns, no maples turning red in autumn, and no apple trees bending under fruit. The forest that began spreading then belonged to a stranger Earth. One of the most famous ancient forest sites is near Gilboa, in New York State. The fossil forest there is about 385 million years old. In the rock, scientists found the bases of trees still arranged where they once grew. Some of those trees belonged to a group called cladoxylopsids. They had tall trunks and crowns of branches that looked somewhat like giant bottle brushes or strange palms. They did not make seeds. They reproduced with spores, tiny reproductive cells that could be carried by wind. A cladoxylopsid tree called Watieza may have grown around 25 feet tall, rising above muddy ground in a world that was still learning how to become a forest. Nearby, other ancient plants were changing the land in different ways. Archaeopteris became one of the most important trees of the late Devonian. It had wood, deep roots, and branches with small leafy structures that looked fern-like. Some Archaeopteris trees may have reached more than 60 feet high, and some estimates place them even taller under good conditions. They were not flowering trees. They were seedless plants, closer in some ways to ferns, yet their trunks could form real wood. A forest of Archaeopteris would have felt familiar from a distance, with vertical trunks and spreading crowns. Up close, it would have seemed almost dreamlike, because the leaves, branches, and life cycles were from vanished plant lineages. The ground under these forests began to change. Earlier, land plants often had shallow roots, so they affected only the upper skin of soil. Deeper roots from tree-like plants pushed farther into sediment and cracked rock. As roots grew, died, and decayed, they helped create thicker soil layers. Soil is more than broken rock. It is a mixture of minerals, dead organic matter, water, air, fungi, and small living things. The first forests helped build that mixture more deeply than earlier plant life could. Shade changed the surface too. A patch of bare ground under direct sun heats and dries quickly. A forest canopy softens that sunlight before it reaches the ground. Under Devonian trees, damp pockets could last longer. fallen branches and dead stems gathered on the forest floor. Small animals, including early arthropods such as mites, millipede-like creatures, and primitive insects, found new spaces to hide, feed, and move. A forest floor became a layered place, with roots below, trunks above, and decaying plant matter between them. Wood also changed the air over long spans of time. As trees grew, they pulled carbon dioxide from the atmosphere. Some carbon returned quickly when plants decayed. Some became buried in wet ground, especially in swamps where low oxygen slowed decay. Buried plant material could hold carbon away from the air for very long periods. Over millions of years, this helped affect Earth's climate. More roots also increased the breakdown of rock, a process called weathering. Weathering can wash minerals into rivers and oceans, and it can help remove carbon dioxide from the air through chemical reactions. A forest, then, was a living force spread across land. It made shade. It deepened soil. It gave animals new shelter. It helped move carbon between air, plants, ground, and water. The Devonian world slowly gained the shape of wooded places, even though those woods were filled with plants unlike the ones we know now. A fallen trunk in that time might lie across damp soil, slowly changing in the quiet. Its cells still held the carbon gathered from ancient air. Its wood still carried the structure made possible by lignin. If burial happened before decay could finish, that material could leave the forest and enter a much longer journey. Some of those ancient plant remains would sink into mud, vanish under layers of sediment, and wait in darkness as Earth turned forests into stone-like fuel. A fallen tree in an ancient swamp could follow a very different path from a fallen tree in a dry forest. On a normal forest floor, dead wood slowly softens. Fungi spread through it. Insects open small tunnels. Bacteria help break down the tissue. Given enough time, much of the carbon returns to the air as carbon dioxide, while minerals and softer remains mix back into the soil. In a swamp, the process can slow dramatically. Water fills the spaces where air would usually flow. Oxygen becomes scarce below the surface. Many of the organisms that break down dead plant material need oxygen to work efficiently, so decay can become incomplete. Leaves, branches, bark, roots, and trunks may pile up in dark, wet layers. Instead of vanishing quickly, they become peat. Peat is the soft brown material that forms when dead plants are partly preserved in waterlogged ground. It can still show traces of stems and leaves. In some bogs today, peat grows only about 1 millimeter or 2 each year. That seems almost still, yet over thousands of years, the layers can become many feet thick. During the Carboniferous period, from about 359 million to 299 million years ago, vast swamp forests spread across parts of what are now North America, Europe, and Asia. The name Carboniferous means coal-bearing. Many of the world's famous coal beds began during this time, when warm, wet lowlands held huge amounts of plant growth. These forests were filled with plants that would look strange now. Tall lycopsid trees, such as lepidodendron, could rise more than 100 feet. Their trunks had diamond-shaped leaf scars pressed into the bark. Giant horsetail relatives, such as calamites, grew in jointed stems near swampy ground. tree ferns spread broad fronds above wet soil. When these plants died, many fell into waterlogged basins where decay slowed and burial could begin. Sediment arrived through floods, rivers, and shifting coastlines. Mud and sand covered the peat. New swamp plants grew above it. Then more plant matter gathered. Layer after layer pressed downward. As burial deepened, the peat was squeezed by weight from above. Water was forced out. The plant material became denser. Over millions of years, heat from Earth's interior and pressure from overlying rock changed its chemistry. The first major coal stage is lignite, a brown, soft coal that still holds more moisture. With more burial and heat, lignite can become bituminous coal, darker and richer in carbon. Under even stronger pressure and heat, it can become anthracite, a hard, shiny coal that burns with very high heat and relatively little smoke. This slow transformation is called coalification. The word simply means the process of becoming coal. It is a long chemical tightening, where buried plant remains lose water, oxygen, and hydrogen, while becoming more concentrated in carbon. A lump of coal held in the hand can look like a plain black rock. Its surface may shine faintly. It may leave dark dust on the fingertips. Inside it, though, is material that began with ancient leaves gathering sunlight. A carboniferous swamp tree used photosynthesis to build its tissues from carbon dioxide and water. That energy came from the sun. When the plant died and became buried before decay could finish, part of that stored energy remained locked away. Coal is ancient plant matter changed by time, pressure, and heat. It is forest memory made dense enough to burn. This is why coal became so powerful for humans much later. During the Industrial Revolution in the 18th and 19th centuries, coal fed steam engines, iron furnaces, trains, factories, and ships. In Britain, coal from places such as Newcastle and South Wales helped power machines that changed daily life across whole nations. The energy released in a furnace had been stored in plant tissue hundreds of millions of years earlier. A flame in a steam engine was touching the sunlight of a vanished swamp. That thought makes ordinary wood feel older and deeper too. A fresh log beside a fireplace and a black seam of coal in the ground belong to the same wider story. Both hold carbon once taken from air. Both carry energy first gathered by living plants. One may burn after a few seasons of drying. The other waited under stone through ages longer than any human history. Wood can hold time in different ways. Sometimes it becomes fuel. Sometimes it becomes coal. Sometimes, inside a standing tree, time remains visible as rings, circling quietly around the center. Inside a trunk, time can leave a shape you can see. A cut log shows this more clearly than almost anything else in nature. Near the center is the oldest wood. Around it, ring after ring spreads outward toward the bark. In places with clear seasons, many trees form one visible growth ring each year. Spring often brings faster growth. The tree has more water, more light, and a fresh season of leaves beginning to open. The cells made during this time are often larger and lighter in color. Later in the growing season, growth slows. The cells may become smaller, denser, and darker. Together, that lighter early wood and darker late wood can mark 1 year of the tree's life. On a freshly cut pine stump, the rings may look like pale bands with thin brown edges. On oak, the rings can be bolder, with larger pores formed early in the season. On maple, they can be more subtle, soft lines circling through pale wood. Each ring is part of the trunk's old work. The tree was standing, lifting water, holding leaves, and adding a new layer under the bark. A wide ring often points to a favorable year. There may have been enough rain. The growing season may have been warm without being too dry. The tree may have had space, light, and healthy roots. A narrow ring can tell a quieter story. Drought can slow growth. Cold springs can delay the start of new cells. Crowding from nearby trees can reduce light. Insects can strip leaves and leave the tree with less energy to build wood. The ring does not speak in words, yet it preserves the effect of those conditions in its width and texture. Scientists study these patterns through dendrochronology. That word means tree-time study. The method works by matching ring patterns from living trees, old beams, dead logs, and ancient wood. A dry year may leave a narrow ring across many trees in the same region. A wet year may leave a wider one. When these patterns overlap, they can be lined up like matching fingerprints. In the American Southwest, tree ring records from long-lived piñon pines, ponderosa pines, and Douglas firs have helped date ancient buildings and cliff dwellings. In Europe, oak beams from old churches, ships, and houses have been matched to long ring records that stretch back centuries. Wood can place a human-made object into a real calendar year. Sometimes the final ring near the bark can show when a tree was cut. That detail can help date a cabin, a shipwreck, or a wooden tool with surprising precision. A trunk can also keep marks from sudden damage. Fire may scar one side of a tree without killing it. If the tree survives, new wood slowly grows around the wound. Years later, the scar appears inside the trunk as a dark, curved mark. In dry forests of western North America, fire scars in old ponderosa pines have helped scientists understand how often low fires once moved across the land. Some fires pass through every few years, clearing grasses and small trees, while older pines survive behind thick bark. Insect outbreaks can leave their own signs. If caterpillars or beetles damage leaves, the tree may make a thinner ring that year because it has less energy from photosynthesis. A spruce growing in a northern forest can record years when cold shortened the growing season. A bristlecone pine high in the White Mountains of California can record harsh years in rings so thin they may be difficult to separate by eye. Some of those bristlecone pines have lived for more than 4,000 years, growing slowly in rocky soil where cold wind limits the season. Their wood is dense, twisted, and patient. Even dead pieces can remain on the dry mountain slopes for thousands of years, allowing scientists to connect living trees with older wood from the same area. This makes tree rings feel almost like a natural archive. The record is quiet, physical, and built one season at a time. A wooden surface may show grain lines that look decorative in a table or floor. Those lines began as growth, weather, light, and stress inside a living trunk. The same material that held a tree upright also kept track of years passing around it. A tree could stand in one place through storms, dry summers, mild springs, insect damage, and fire, then carry those events inside its wood. This record helps explain why humans came to value wood so deeply. It held weight. It could be shaped by hand. It stored the history of the living tree within a material people could cut, carry, carve, and build with. The rings inside a trunk show time, and the cells inside those rings explain why wood feels so useful in the hand. A dry board can seem solid when you tap it with your knuckles. The sound may be firm, warm, and low. Yet much of wood's strength comes from a structure filled with tiny empty spaces. During the life of the tree, many wood cells were long tubes or narrow chambers. Some carried water. Some helped support the stem. After a tree is cut and dried, many of those cells no longer contain living fluid. They become small hollow spaces surrounded by strong cell walls. This is one reason wood can be surprisingly light for its strength. A piece of pine framing lumber can be carried on one shoulder, even though it may later hold part of a wall or roof. A steel beam of similar size would be far heavier. Wood gets much of its usefulness from this balance. It has strong walls arranged around open space, somewhat like a bundle of tiny drinking straws packed tightly together. A straw by itself bends easily. Many straws joined in the same direction become harder to crush from end to end. Wood works in a similar way, although its structure is far more complex. The long cells inside a tree mostly run up and down the trunk. That direction becomes the grain. Grain is the visible path of the wood fibers, and it affects almost everything people do with wood. A board is usually strongest along the grain. That means it can resist pulling and bending better when the force follows the length of the fibers. Across the grain, the wood behaves differently. It may split more easily because the fibers can separate from each other. This is why a log can be split with an axe along its length. The axe edge follows the natural direction of the cells. Trying to chop cleanly across a thick log takes more effort, because the blade has to cut through many fibers instead of opening between them. Carpenters, boat builders, instrument makers, and furniture makers have always paid attention to grain. A chair leg needs strength along its length. A bow made from yew or Osage orange depends on wood that can bend and spring back without breaking. A violin top, often made from spruce, needs wood that is light, stiff, and able to vibrate clearly. The same material can become a roof beam, a tool handle, a canoe paddle, or a soundboard because the grain can be chosen and shaped for different jobs. Density also matters. Density means how much mass is packed into a certain volume. Balsa wood is famous for being extremely light. It comes from Acroma pyramidale, a fast-growing tropical tree native to the Americas. Its wood has large cells with thin walls, so it can feel almost foam-like compared with heavier woods. That is why balsa has been used in model airplanes, floats, and lightweight cores in certain composite materials. At the other end, lignum vitae is so dense that some pieces can sink in water. Its name means wood of life, and it was once used for ship parts, pulley wheels, and bearings because it is heavy, oily, and resistant to wear. Between those extremes sit familiar woods like pine, oak, maple, cedar, and walnut. Each has its own balance of cell size, wall thickness, grain pattern, and natural chemicals. A white pine board feels light and easy to cut. A hard maple board feels heavier, smoother, and more resistant under a tool. Oak often shows larger pores, giving it a strong open grain. Cedar may feel light and carry a clear scent because of oils stored in the wood. This variety gave humans a wide material library long before modern manufacturing. A branch could become a handle. A straight trunk could become a post. A wide plank could become a door or table. Wood could be worked with stone blades, bronze tools, iron axes, steel saws, and modern machines, because it is strong enough to serve and soft enough to shape. That combination is rare. Stone can be durable, yet shaping it takes heavy effort. Bone and antler can be useful, yet they come in limited sizes. Wood grows in long pieces, curved pieces, dense pieces, light pieces, and sheets that can be split from larger trunks. A forest quietly offers material in many forms. The hollow cells, long fibers, and directional grain made wood one of the first great substances humans could truly work with. Long before advanced metals, people learned that a tree could become shelter, tools, warmth, and movement. That is where the human story with wood begins to deepen. Long before advanced metals, people had trees within reach. A fallen branch could become a digging stick. A straight sapling could become a spear shaft. A thicker limb could become a handle for stone, bone, or later metal. Wood offered length, shape, and strength in ways early people could understand by touch. Its grain showed which way it wanted to split. Its weight told whether it was dry or wet. Its smell changed when it was fresh, burned, or softened by age. Because wood decays so easily, most ancient wooden objects have disappeared. Stone tools survive in dry caves, river gravels, and buried campsites for hundreds of thousands of years. Wood usually returns to soil unless it is sealed in water, frozen ground, peat, or very dry shelter. That makes the surviving pieces especially valuable. They are rare windows into a material people almost certainly used every day. At Schöningen in Germany, archaeologists found wooden spears about 300,000 years old. They were made from spruce and carefully shaped, with the thickest weight placed forward, a little like a modern javelin. These were not random sticks picked up from the ground. They were planned hunting weapons, smoothed and balanced by hands that understood wood well. At Clacton-on-Sea in England, an older wooden spear point has been dated to roughly 400,000 years ago. At Kalambo Falls in Zambia, ancient shaped logs about 476,000 years old show that early human relatives were working wood in a more structural way. Hominin is the word scientists use for humans and our close extinct relatives. These hominins shaped large pieces of wood long before cities, writing, or farming existed. Wood fit the human hand. A stone flake can be sharp, but it is small and hard to grip safely. Attach that flake to a wooden handle, and the tool changes. The hand gains reach. The edge gains force. The same idea appears again and again across human history. A stone axe head becomes more useful when mounted on a wooden haft. A digging stick becomes more effective when its point is hardened in fire. A wooden spear lets the body keep distance from danger. Many early tools were combinations of materials, and wood was often the part that made the tool usable. Shelter also leaned on wood. Branches could form frames. Poles could hold hides, bark, grass. or woven mats. In forested regions, people could bend flexible saplings into arches or lean straight poles into simple supports. Wood was easier to shape than stone because it could be cut, scraped, split, shaved, drilled, and tied with plant fibers or sinew. If a wooden tool broke, a person could often repair it, shorten it, bind it, or make another from nearby material. That mattered in daily life. A broken stone blade might need special rock from a certain place. A broken branch could often be replaced from the edge of a woodland. Wood also gave people containers and surfaces. Hollowed logs could hold water or food. Bark could be peeled in sheets from birch, cedar, or other trees and turned into coverings, baskets, or simple vessels. In northern forests, birch bark became especially useful because it is light, flexible, and water-resistant. Indigenous peoples across parts of North America used it for canoes, containers, and shelters. A birch bark canoe could move quietly across lakes and rivers, carrying people and goods through landscapes where roads did not exist. Trees also gave long straight pieces in many sizes. Bone and antler are useful, strong materials, yet their size is limited by the animal they come from. A forest can grow poles, planks, branches, roots, bark, and fibers. A single mature tree can offer more usable length than almost any animal material. This made wood a natural partner for building, carrying, hunting, cooking, and traveling. A person could look at a tree and see many future objects hidden inside it. The trunk might become a post. The branch might become a bow. The root might become a curved handle. The bark might become a covering. Each part had its own quiet use. Wood became humanity's first great material because it was strong enough to serve and gentle enough to shape. It stood between the living forest and the working hand. Once people learned how to cut it, carve it, bind it, and bend it, trees became tools, shelters, containers, and paths across water. Yet wood held another power inside its fibers. The same sunlight that helped build the trunk could be released again as heat, light, and flame. The same tree that could become a handle, a spear, or a shelter pole also carried hidden energy inside its fibers. That energy began in sunlight. When a tree grows, its leaves catch light from the sun and use that light to build sugars from carbon dioxide and water. Some of those sugars become cellulose, hemicellulose, and lignin inside the wood. As long as the tree stands, that energy is stored quietly in the trunk and branches. When dry wood burns, oxygen from the air reacts with those carbon-rich materials. The reaction releases heat, light, water vapor, carbon dioxide, smoke, and ash. A flame is the stored work of a tree returning to the air as warmth. Wood does not burn well when it is full of water. Freshly cut wood can contain a large amount of moisture, sometimes more than half its weight depending on the species and season. Before a log burns strongly, heat has to drive much of that water away as steam. Dry wood catches more easily because less energy is wasted boiling off moisture. As wood gets hot, often around a few hundred degrees Celsius, its solid materials begin to break apart and release gases. Those gases burn above the surface, creating the yellow and orange flames people see in a campfire or hearth. For early humans, That glow changed the night. Fire pushed back cold. It lit the ground after sunset. It made caves, camps, and shelters safer by keeping many animals away. It also changed food. Cooked meat becomes easier to chew. Cooked roots and tubers become softer. Heat can break down tough plant tissues and make some foods easier for the body to digest. Cooking also kills many harmful microbes and parasites that can live in raw food. A wood fire, then, was more than a bright center in a dark camp. It changed what humans could eat, how much energy they could gain from food, and how far they could live from naturally warm places. Evidence for ancient fire use reaches deep into prehistory. At Wonderwork Cave in South Africa, burned bone and plant ash suggest fire was being used there around 1 million years ago. At Gesher Benot Yaakov in Israel, burned flint and plant remains show repeated fire use roughly 780,000 years ago. These are very old traces, and they show how deeply fire belongs to the human story. The wood itself rarely survives from such fires. What remains are ash, reddened sediment, charred fragments, and tools changed by heat. Still, the pattern is clear. Where humans learned to manage burning wood, they gained warmth, cooked food, and a gathering place after dark. Later, people discovered that wood could be changed before it was burned. Charcoal is made when wood is heated with very little oxygen. In that low oxygen setting, much of the water and smoky material leaves the wood, while a carbon-rich solid remains. Charcoal is lighter than raw wood, darker and often brittle. It burns hotter and with less smoke because many of the volatile compounds have already been driven away. That made charcoal extremely useful for crafts that needed higher heat. Pottery kilns, glassmaking, and metalworking all depended on steady, intense fire. In early iron production, furnaces called bloomeries used charcoal to reach the high temperatures needed to separate iron from ore. A bloomery did not melt iron into a liquid like a modern blast furnace. It produced a spongy mass of iron and slag that had to be hammered into shape. Even so, charcoal gave people a way to turn reddish rocks and dark ores into tools, blades, nails, hinges, and plows. A quiet piece of burned wood helped open the age of metal. The path from a tree branch to a forge is long, but the connection is direct. Wood gathered sunlight. Fire released the stored energy. Charcoal concentrated that energy into a cleaner, hotter fuel. From that heat came cooked meals, hardened clay, shaped metal, and new forms of shelter and work. Wood became power in the most literal sense. It warmed bodies, changed food, hardened tools, and lit human spaces after the sun had gone down. Once people learned to build with wood and burn it with care, entire ways of life could grow around forests. Homes, roads, ships, carts, barns, workshops, and villages began to depend on the material that trees kept making season after season. Around the warmth of fire, human life kept finding new uses for trees. A forest could become a village piece by piece. Straight trunks became posts. Split boards became walls. Branches became fence rails, roof supports, ladders, handles, and simple frames for daily work. For much of human history, wood was one of the main materials holding the built world together. Stone was strong, yet heavy and slow to shape. Metal was powerful, yet difficult to mine, smelt, and forge. Wood grew nearby in many places, already raised by the tree into long beams and useful shapes. A person with an axe, a wedge, and time could turn a trunk into shelter. In many parts of northern Europe, timber-framed houses used heavy wooden beams joined with carved connections. One common joint, called a mortise and tenon, worked by fitting a projecting end of one beam into a matching hole in another. Wooden pegs could lock the pieces together. These frames could stand for centuries when kept dry and repaired. Some medieval timber buildings in England, Germany, and France still show their old beams, darkened by age and smoke, with the grain visible beneath the surface. Roofs also depended on wood. Rafters carried the weight of thatch, shingles, clay tiles, or later slate. In snowy regions, roof beams had to resist heavy winter loads. In rainy regions, wide eaves helped keep water away from walls. A wooden roof was a quiet piece of engineering, shaped by local climate and local trees. Oak, chestnut, pine, fir, spruce, cedar, and larch all found different places in building traditions. The wooden world also moved on wheels. Carts and wagons carried grain, hay, stone, firewood, barrels, and people along rough roads. Before rubber tires and steel frames, many wheels were made with wooden hubs, wooden spokes, and wooden rims, sometimes strengthened with an iron tire around the outside. A wheelwright, the craftsperson who made wheels, had to understand how different woods behaved. Elm could be used for hubs because it resisted splitting. Oak made strong spokes. Ash bent well and could take repeated strain. Daily storage relied heavily on wood too. Barrels were one of the great inventions of the wooden age. A barrel is made from curved boards called staves, held together by hoops. The shape is strong, rollable, and able to hold liquids or dry goods. Romans used barrels widely, especially in the northern parts of their empire where wooden containers were common. For centuries, barrels carried wine, beer, salted fish, flour, oil, gunpowder, and water. A ship, cellar, market, or mill might be filled with them. The craft of barrel making, called cooperage, required careful shaping, so the staves pressed tightly together and sealed without glue. Furniture grew from the same practical skill. A stool, chest, cradle, table, bench, bed frame, and door could all be made from boards and joined pieces. Many objects now made from plastic or metal once came from wood. Buckets, bowls, spoons, combs, toolboxes, toys, handles, washboards, window frames, and storage chests all carried the feel of grain under the hand. A household in the year 1200 or 1600 would have been surrounded by wood in ways that are easy to forget now. Even construction with stone often depended on timber. Wooden scaffolding let workers reach high walls. Wooden centering supported arches while stone blocks were being placed. Mines used timber supports to hold back earth and rock. Bridges crossed streams and rivers on wooden piles, beams, and decks. In Japan, the Horyuji temple complex includes wooden buildings with parts dating back more than 1,300 years, showing how carefully chosen timber and skilled joinery can survive across astonishing spans of time. The reason wood became so common was practical. Forests stood near many settlements. Trees could be cut, moved, split, carved, bent with steam, and replaced by new growth when forests were managed well. A village did not need a distant factory to use wood. It needed knowledge, tools, and access to trees. This made wood feel close to life. It came from the edge of fields, from hillsides, from river valleys, from nearby woodland paths where people gathered fuel and selected trunks for building. For thousands of years, the human world rested on this quiet material. It held roofs above sleeping families. It carried harvests along roads. It stored food through winter. It supported workers as they built in stone. The dependence grew even larger when people looked toward rivers, lakes, and open sea. A tree rooted in soil could become something that floated, carried weight, and moved beyond the shore. Once people learned that wood could float, the forest gained a new kind of motion. A trunk that once stood fixed in soil could become a canoe, a raft, a river barge, or a ship crossing open water. This worked because many kinds of wood are less dense than water. Density means how much matter is packed into a certain amount of space. When dry wood holds enough tiny air spaces inside its cells, it can float even while carrying weight. A simple dugout canoe could be made from one large trunk. People shaped the outside, hollowed the inside, and turned a tree into a narrow vessel. Dugout canoes have been found in many parts of the world, including Europe, Africa, Asia, and the Americas. The Pessie canoe from the Netherlands, often dated to around 8,000 years ago, was made from a Scots pine trunk. It is one of the oldest known boats ever found. A single-shaped tree could carry a person across a lake or along a slow river. Larger ships required a whole forest. A wooden sailing ship needed curved ribs to form its skeleton. It needed long planks for the outer hull. It needed heavy beams for decks. It needed tall, straight trunks for masts. It needed smaller pieces for oars, blocks, rails, ladders, doors, and storage spaces. Different parts of the ship often needed different trees. Oak was valued for strength and curved branches that could become natural ship ribs. Pine, fir, and spruce were valued for long, straight masts. Teak became famous in tropical shipbuilding because its natural oils helped resist rot and marine worms. In the 18th century, the British warship HMS Victory required thousands of trees, often described as about 6,000, most of them oak. It was launched in 1765 and still survives today in Portsmouth, England. Its great wooden hull shows how much living forest could be gathered into one floating structure. The scale becomes even easier to picture when imagining a shipyard before steel. Logs lie stacked near the water. Carpenters shape curved timbers with axes and adzes. An adze is a cutting tool with a blade set across the handle, useful for smoothing and hollowing wood. Planks are heated, bent, and fastened into place. Tar, pitch, or other sealants are pushed into seams to keep water out. Iron nails or wooden pegs hold parts together. The smell would be sharp with resin, sawdust, wet rope, smoke, and salt air. Ships connected forests to the wider world. Fishing boats carried people to offshore waters where cod, herring, tuna, and other fish could be caught in larger numbers. Riverboats moved grain, timber, salt, pottery, and cloth between inland towns. Merchant ships crossed the Mediterranean, the Indian Ocean, the North Atlantic, and the Pacific with cargo packed below deck. Migration followed wooden hulls too, from island voyages in the Pacific to crowded Atlantic crossings centuries later. War also depended on timber. Fleets were built from trees before steel armor and engines changed naval power. A kingdom with access to strong forests, skilled shipwrights, and good harbors had a deep advantage. In Scandinavia, Viking longships used overlapping planks in a style called clinker building. The planks were fastened edge over edge, making the hull flexible and light. These ships could cross rough seas and also move up shallow rivers. In the Pacific, Polynesian voyagers built large double-hulled canoes using wood, plant fiber cordage, and careful knowledge of stars, winds, currents, birds, and waves. Their vessels carried people across enormous distances of open ocean long before modern navigation instruments. A ship, made from wood, was more than a tool for travel. It was a forest rearranged into ribs, skin, spine, and sail. It held the strength of trunks, the flexibility of grain, and the buoyancy of hollow cells. It carried human plans far beyond the tree line. Wooden ships changed what distance meant. A river became a road. A coastline became a path. An ocean became something dangerous, immense, and still crossable. All of this came from the same material that could also become a table, a beam, a bow, or a barrel. The more people worked with wood, the more they learned that every species had its own nature. Some woods floated lightly, some bent without breaking, some resisted water, some held a carved edge or carried a clear tone through the body of an instrument. The forest was never offering one single material. It was offering many kinds of wood, each with its own weight, grain, scent, color, and quiet behavior. That quiet behavior becomes clear the moment two pieces of wood are placed side by side. A pale strip of balsa can feel almost weightless in the hand. A dark piece of ebony can feel dense, cool, and heavy, almost like polished stone. Both came from trees. Both are wood. Yet their bodies grew with very different inner structures. Balsa comes from a fast-growing tropical tree called Acroma pyramidale, native to parts of Central and South America. Its wood has large cells with thin walls, leaving a great deal of open space inside. That gives balsa its famous low density. Density is the amount of material packed into a certain space. A block of balsa may weigh only a small fraction of the same size block of oak or maple. This is why balsa became useful for model airplanes, floats, surfboard cores, and lightweight craft projects. It can be cut with a small blade and lifted with almost no effort. At the other extreme is lignum vitae, a very dense wood from trees in the Guaiacum genus. Some pieces are dense enough to sink in water. The wood contains natural oils, giving it a waxy feel and making it resistant to wear. For a long time, lignum vitae was used in ship bearings, pulley wheels, and parts that needed to slide under pressure. Before modern plastics and metal alloys took over many of those jobs, this heavy tropical wood did work that sounds almost mechanical. Ebony carries another kind of presence. True ebony comes from trees in the Diospyros genus. Its heartwood can be deep black or dark brown, with a fine, smooth texture. Because it is dense and takes a polish well, Ebony has been used for piano keys, violin fingerboards, carved objects, and decorative inlay. A small piece of ebony can feel heavy for its size, as if the tree packed years of growth into a very tight space. Other woods announce themselves through scent. Cedar is one of the most familiar examples. Western red cedar, eastern red cedar, and true cedars are different trees. Yet many cedar-like woods contain aromatic oils that create a strong, clean smell. Those natural chemicals can help resist insects and decay. A cedar chest was often used to store blankets, clothing, or wool, because the scent helped discourage moths. Fresh cedar boards can fill a workshop with a sharp, warm fragrance as soon as the saw opens the grain. Maple offers a calmer surface. Hard maple, often from the sugar maple tree, Acer saccharum, has pale wood with a fine, even grain. It is hard enough for flooring, bowling alley lanes, cutting boards, and furniture that must handle repeated use. Sugar maple is also the tree tapped for maple syrup in eastern North America. In late winter and early spring, sap flows through the tree when freezing nights and warmer days create pressure changes inside the trunk. The same species can offer sweet sap in the forest and smooth pale boards in a workshop. Oak has a stronger visible pattern. Many oaks are ring porous, meaning they form larger water vessels early in the growing season. Those vessels show up as open pores and bold grain lines. White oak has special growths called tyloses that can block many of its vessels. Because of this, white oak can hold liquid well. Coopers, the craftspeople who make barrels, have long used white oak for wine, whiskey, and other aging liquids. Inside a barrel, the wood slowly shares flavor compounds with the drink. Vanilla-like notes, toasted aromas, and tannins can come from the oak as the liquid rests for months or years. Red oak, by contrast, has more open pores. If air is blown through one end of a short red oak board, bubbles can sometimes appear from the other end when it is placed in water. That small demonstration shows how differently two related woods can behave. A forest, then, is a library of materials grown slowly in trunks and branches. Some woods are chosen for lightness. Some are chosen for smell. Some are chosen for hardness, color, grain, or resistance to water. Human hands learn these differences through building, carving, burning, bending, and listening. Yet the names used for wood can create their own confusion. The familiar words hardwood and softwood sound simple, while the trees behind them follow a more surprising rule. The words hardwood and softwood sound as if they belong to the hand. A heavy oak plank feels like hardwood. A pale pine board feels like softwood. That simple feeling works often enough to make the name seem obvious. The real meaning comes from the kind of tree that made the wood. Hardwoods usually come from flowering trees. These trees are called angiosperms. An angiosperm is a plant that makes seeds enclosed inside flowers, fruits, nuts, or other protective structures. Oak, maple, walnut, cherry, birch, ash, beech, poplar, and mahogany all belong to this broad group. Some drop wide leaves in autumn. Some grow in tropical forests and keep leaves through the year. Many form flowers that may be small and easy to miss. An oak flower looks nothing like a garden rose, yet the oak still belongs among flowering plants. Softwoods usually come from conifers. Conifers are trees that make seeds in cones or cone-like structures. Pine, spruce, fir, cedar, hemlock, larch, and redwood are familiar examples. Many have needles or scale-like leaves. Many stay green through winter, which is why people often call them evergreens. A pine cone holding seeds beneath woody scales is a quiet clue to the tree's group. The label follows reproduction, structure, and ancestry more than surface feel. Inside the wood, hardwoods and softwoods often have different kinds of cells. Many hardwoods contain vessel elements, which are wider water-carrying cells that can form visible pores. That is why oak, ash, and elm often show a stronger open grain. Softwoods usually lack those large vessels. Their wood is built mostly from long cells called tracheids, which help carry water and support the trunk at the same time. This gives many softwoods a more even texture. A smooth pine board may show clear growth rings, pale early wood, and darker late wood, with fewer large pores than oak. The names can still surprise people. Balsa is a hardwood because it comes from a flowering tree. Its wood is among the lightest used by humans. A balsa block can be pressed with a fingernail and cut with a small craft knife. Yet botanically, it sits with hardwoods. Aspen and basswood are also hardwoods, and both are fairly soft and easy to carve. Basswood has long been used for wood carving because its pale grain is gentle under a blade. Some softwoods can be quite strong or dense. Southern yellow pine, a group that includes species such as longleaf pine, can be tough, resinous, and useful for heavy construction. Douglas fir, often grouped with softwoods in the lumber trade, is valued for beams, framing, and plywood because it combines strength with long, straight grain. Yew, a conifer, has dense, elastic wood that was historically prized for longbows in medieval Europe. A bow needs wood that can bend, store energy, and return without snapping. Yew did that so well that it became one of the most famous bow woods in history. This shows how much more there is to wood than a label. A furniture maker may care about hardness, grain, color, movement, and how the wood takes finish. A builder may care about strength, straightness, cost, and resistance to decay. A carver may want softness and even texture. A boat builder may look for rot resistance, bend, and stability near water. The word hardwood gives a starting point. The word softwood gives a starting point. The real choice comes from the tree species and the way that particular piece grew. Even within one species, conditions matter. A tree grown slowly in a cold, crowded forest may make tighter rings. A tree grown quickly in open light may form wider rings. Knots appear where branches were once joined to the trunk. Reaction wood can form when a tree grows on a slope or leans toward light, creating areas that shrink and bend differently later. A board from near the center of a trunk may behave differently from one cut closer to the bark. The living history of the tree remains inside the lumber. That history continues after cutting. A board may look finished after it leaves the sawmill, stacked neatly with sharp edges and fresh pale surfaces. Inside it, water is still leaving. The cell walls are still adjusting. The grain is still able to swell, shrink, cup, twist, or split as the surrounding air changes. Wood keeps answering the world around it long after the tree has been felled. A board can leave the sawmill with clean edges, square corners, and the smell of fresh grain. Yet its quiet changes are still underway. Freshly cut wood is often called green wood. That means it still holds much of the water it carried inside the tree. Some of that water sits in the hollow spaces of the cells. Some is bound inside the cell walls themselves. In a living tree, this water helped move minerals, keep tissues active, and support the flow between roots and leaves. After the tree is cut, the water begins to leave. A fresh log may feel heavy because of this hidden moisture. A newly cut oak or maple log can weigh far more than the same log after months of drying. Softwoods used for house framing are often dried until they reach a moisture content around 19% or lower. Furniture wood is usually dried further, often closer to 6 to 8% for indoor use. Moisture content simply means how much water is in the wood compared with the dry weight of the wood itself. The drying process has to happen with care. If the outside of a board dries too quickly, while the inside remains wet, the surface can shrink and crack. That is why lumber is often stacked with thin strips of wood between the boards. These strips are called stickers. They create small air spaces so moisture can leave more evenly. In modern sawmills, wood may also be dried in kilns, which are heated chambers where temperature, air movement, and humidity are controlled. Kiln drying can take days or weeks. Air drying outside can take many months, depending on the thickness of the boards, the species of tree, and the local climate. Wood begins to shrink most noticeably after it reaches a point called the fiber saturation point. This usually happens around 25 to 30% moisture content. Above that point, water is mostly leaving the hollow cell spaces. Below that point, water begins leaving the cell walls, and the walls themselves start to contract. This is where wood movement becomes important. Wood shrinks very little along the length of the grain. A long board may change only a tiny amount from end to end. Across the grain, the movement is much larger. Tangential shrinkage, which follows the curve of the growth rings, is often roughly twice as much as radial shrinkage, which moves from the center of the tree outward. That difference helps explain cupping. A flat board cut from a log may bend slightly as it dries because one part is shrinking more than another. The surface can curve like a shallow dish. Cracks can open at the ends of boards because moisture leaves quickly through exposed end grain. A round log may split from the outside inward as it dries, forming deep checks along its length. Woodworkers slow this by sealing the ends of fresh boards or logs with wax, paint, or special coatings. Even after wood is dried, shaped, sanded, and finished, it keeps responding to the air. A wooden floor may open small gaps during a dry winter, when indoor heating lowers humidity. In summer, when the air carries more moisture, the boards may swell and press closer together. A solid wood door may stick during damp weather because its fibers have taken in water vapor from the air. An old table can move slightly through the seasons. even if it has stood in the same room for decades. This movement is one reason traditional furniture often uses careful joinery. A tabletop may be fastened in a way that allows it to expand across its width. A cabinet door may use a floating center panel, giving the wood space to move inside the frame. These details are quiet forms of respect for the material. Wood came from a living tree, and its cell walls still react to moisture long after growth has ended. A board may be cut away from roots, leaves, and bark, yet the structure inside it keeps remembering water. It opens and closes with the weather. It bends slightly under changing air. It carries the habits of the trunk into the rooms, floors, instruments, and tools humans make from it. And when wood is left outside, where rain, soil, fungi, and insects can reach it, those slow changes become part of a larger return. The same material that once rose upward in a tree begins moving back into the forest. Outside, under rain and shade, wood follows a different path than it does inside a dry room. A floorboard may last for generations when it is kept away from moisture. A fallen log on a forest floor begins answering to water, soil, insects, and fungi. The change can start quietly. Bark loosens. The cut ends darken. Small cracks open along the grain. Moss may settle on the upper surface where rain lingers. Underneath, where the log touches damp soil, the wood softens first. Decay is not just damage. It is the forest slowly taking back the material a tree once built. Fungi are especially important in this return. A fungus is a living organism that feeds by releasing chemicals into its surroundings and absorbing the broken down material. Mushrooms are only the visible fruiting bodies of some fungi. Most of the fungus lives as thin threads called hyphae. These threads can spread through wood like pale hair, moving through tiny cracks and cell spaces. Together, many hyphae form a network called mycelium. Inside dead wood, that network releases enzymes. Enzymes are tiny biological tools that help break large molecules into smaller pieces. Wood is difficult to digest because cellulose and lignin are tough substances. Many organisms can break down cellulose. Lignin is much harder. Its structure is complex, irregular, and resistant. White rot fungi are among the few life forms that can break lignin down effectively. Species such as turkey tail, which grows in thin fan-shaped shelves, and oyster mushrooms, which can appear in soft clusters on dead trunks, help open wood's strongest chemistry. Brown rot fungi work differently. They break down much of the cellulose and hemicellulose, while leaving more lignin behind. Wood affected by brown rot can become dry, dark, and crumbly, sometimes breaking into cube-like pieces. White rot often leaves wood paler, stringier, and softer because more lignin has been removed. Both kinds of decay change a firm trunk into something the forest can use again. A fallen beech log in a cool eastern forest may take decades to break down. A pine log in a dry place may last much longer. In warm, wet forests, decay can move faster because moisture and heat support fungi, bacteria, and insects. The pace depends on species, temperature, rainfall, bark thickness, wood density, and contact with soil. A dense oak log resists longer than a soft poplar branch. Cedar can last because its aromatic chemicals discourage many decomposers. As fungi work, carbon leaves the wood in different ways. Some returns to the air as carbon dioxide when organisms breathe. Some stays in fungal tissue, insect bodies, soil particles, and dark organic matter. Nutrients such as nitrogen, phosphorus, calcium, and potassium move back into the forest floor. New roots can later take them up. A mineral that once helped build leaves may pass into soil, then into a seedling, then into another ring of wood. Rot makes the forest circular. The fallen trunk becomes darker, wetter, and more open. Rainwater gathers in softened pockets. Beetles enter through cracks. Ants may use older tunnels. Small roots grow along the surface. Ferns and mosses can anchor in the damp wood as if it were raised soil. In old forests of the Pacific Northwest, large decaying logs are sometimes called nurse logs because young hemlock, spruce, and cedar seedlings grow on top of them. The log lifts the seedlings above deep shade and wet litter. As it decays, it slowly feeds the new growth it carries. A standing tree once lifted leaves into sunlight. After falling, its wood can hold moisture, shelter small life, and return stored carbon to the living ground. The same fibers that once resisted gravity gradually loosen. The same lignin that helped a trunk stand tall becomes food for specialized fungi. A log on the forest floor is a slow transformation, measured in seasons, rainstorms, spreading threads, and softening rings. As the wood opens, it becomes less like a finished object and more like a small landscape. Within that landscape, many lives begin to move through the spaces left behind. Within the softened wood, small lives begin to use the spaces that decay has opened. A fallen log may look quiet from a few steps away. Its bark may be dark with rain. Its upper side may hold a strip of green moss. Along the lower edge, where the wood touches soil, tiny openings can lead into a hidden world. Beetles are often among the first animals to enter dead or weakened wood. Some bark beetles tunnel beneath bark, leaving thin winding galleries that look like little maps carved into the inner surface. Longhorn beetle larvae can chew deeper into trunks and branches, slowly widening their passages as they grow. The larvae are pale, soft-bodied young insects, and many spend months or years inside wood before becoming adults. Their tunnels let air, moisture, fungi, and bacteria move farther into the log. A hole made by one insect becomes an entrance for other forms of decay. Termites play an even larger role in warm regions. They can digest cellulose with help from microbes living inside their bodies. Those microbes break down plant material that the termite could not handle alone. In tropical forests and savannas, termites recycle enormous amounts of dead wood and dry plant matter. Their nests and tunnels move nutrients through soil, and their feeding helps return old trunks to the living system around them. Carpenter ants use wood differently. They do not eat the wood as food. They carve galleries into damp or decayed wood to build nests. A rotting stump can become a sheltered ant city, with chambers hidden behind bark and softened grain. Fungi continue their quiet work around all of this movement. Mushrooms may rise from the log after rain, appearing for only a few days before fading. The main fungal body remains inside, threaded through the wood. Bacteria also live in the damp spaces, helping process smaller compounds and changing the chemistry of the decaying tissue. On the surface, mosses and liverworts can hold water like little sponges. A log lying in shade can stay moist long after the surrounding leaves have dried. That moisture makes it useful to animals that need cool, protected places. Salamanders often hide under logs because their skin must stay damp. Small snakes may rest beneath them for cover. Mice and voles can use hollows as pathways or shelters. In colder months, some insects overwinter inside cracks where the temperature changes more slowly than in open air. Standing dead trees, called snags, are just as important. A snag may look bare against the sky, with broken branches and peeling bark. Inside it, the wood can be soft enough for birds to carve. Woodpeckers use their strong bills to dig nesting cavities in dead or dying trunks. A pileated woodpecker can make a large oval hole in a tree, sometimes big enough for other animals to use later. Smaller woodpeckers, such as downy woodpeckers, make tighter cavities. After the original bird leaves, those holes may become homes for chickadees, nuthatches, tree swallows, flying squirrels, bats, or owls. Many animals depend on cavities, yet cannot carve them for themselves. The woodpecker becomes an engineer of shelter for the wider forest. Dead wood also protects new growth. A decaying log can hold water through dry weeks. Seeds may land in moss on its surface. Fine roots can grow into the softened wood and draw from the moisture stored there. In old temperate rainforests, young trees often sprout in rows along nurse logs. Years later, when the old log has mostly disappeared, the younger trees may stand in a straight line, marking the shape of the wood that once held them up. This is one reason forests need dead material as well as living trees. A clean forest floor may look neat to human eyes, yet too much cleaning removes shelter, food, and moisture. Dead branches, hollow trunks, stumps, and snags create layers of habitat. They support insects that feed birds. They hold fungi that recycle nutrients. They give small animals places to hide from heat, cold, and predators. A fallen tree becomes part of the forest's memory in a physical way. Its wood still contains carbon gathered from the air. Its minerals return slowly to soil. Its hollow spaces become rooms for lives too small or quiet to notice at first glance. This makes human use of wood feel more complicated. A tree can become a beam, a table, a page, or a warm fire. Within a forest, that same tree could have become a home for beetles, fungi, moss, birds, and seedlings. Using wood means touching a living system that reaches beyond the trunk itself. A forest can grow back, yet wood is renewable only when time is allowed to do its work. A pine seedling may reach usable pulpwood size in 20 or 30 years. An oak grown for strong beams may need many decades. A giant sequoia can live for more than 3,000 years, and an old-growth cedar forest may take centuries to regain the structure it once had. The word renewable can make wood sound simple. A tree is cut. A new tree is planted. The material returns. Real forests move on slower clocks. Roots need soil that has not been washed away. Seedlings need enough light, water, and protection from grazing animals. Fungi need old logs and damp ground. Birds, insects, and small mammals need layers of shelter that young tree farms do not always provide. A forest is more than standing trunks. It is living soil, fallen wood, shade, roots, seeds, and the quiet exchange of nutrients through many forms of life. Human history shows how quickly usable timber can become scarce in one place. In ancient Mesopotamia, cities such as Ur and Babylon needed wood for roof beams, boats, tools, carts, kilns, and fuel. Much of the region had little large timber nearby, so people imported cedar and other valuable woods from mountain regions, including the famous cedar forests of Lebanon. Those cedar forests were cut for ships, temples, palaces, and trade across thousands of years. Small protected groves still remain today, but the ancient forests that once covered larger mountain areas were greatly reduced. The story repeated in different forms around the world. Shipbuilding placed enormous pressure on forests. A large wooden warship needed thousands of mature trees. In Britain, by the 1600s and 1700s, good ship timber became a serious national concern. Oak trees suitable for curved ship ribs and long planks took many decades to grow. The Royal Navy depended on huge supplies of oak, pine, fir, and imported Baltic timber. Forests were no longer simply nearby woodland. They became strategic resources tied to trade, war, and state power. Japan faced its own timber pressure during the early Edo period. Castle building, city growth, fires, and agriculture increased demand for wood during the 1600s. Large areas were heavily cut. Over time, forest rules, planting systems, and controlled harvesting became more important. This did not make every forest untouched, but it showed a practical lesson. A society can run short of wood long before trees vanish completely. The shortage begins with the right size, species, quality, and location of timber. A hillside may still have trees, while lacking the straight old trunks needed for beams, masts, or durable boards. Modern forestry can produce large amounts of wood through plantations. A plantation is a managed area where trees are planted and harvested like a crop. Fast-growing eucalyptus, pine, spruce, and poplar can supply paper pulp, cardboard, lumber, and engineered wood. Some plantations are very efficient. Rows of young trees may grow evenly, with trunks spaced for machinery and harvesting. This can reduce pressure on wild forests when managed carefully. Plantations also have limits. A stand of one tree species, all the same age, does not hold the same life as an old mixed forest. An old forest may contain standing dead trees, fallen logs, young saplings, deep leaf litter, hollow trunks, fungi, birds, beetles, mosses, and shaded streams. Those layers build slowly. A fast-growing tree farm can make useful wood in a few decades. An ancient forest structure can take centuries to form. This is why the question of running out of wood has two answers. Humanity can grow more wood. Local regions can still lose the kind of wood they need. A country can import timber, while its own old forests shrink. A company can plant new trees while rare habitats disappear. The future of wood depends on matching human appetite with forest time. Careful harvesting, longer rotations, protected old-growth areas, recycled wood, and better building design all help reduce waste. A board used for a century in a house stores carbon far longer than a branch burned in an afternoon. A beam reused from an old barn carries its material life forward again. Wood asks for a slower kind of thinking. The tree grows through seasons. The forest gathers complexity through generations. The deeper issue is whether modern society can keep using this generous material while protecting the living systems that make it possible. Modern cities often look as if they have moved beyond the forest. Steel columns rise inside towers. Concrete foundations hold streets, bridges, schools, hospitals, and apartment blocks. Glass covers walls in clean reflective sheets. Yet wood remains close to the center of human building. It appears in roof frames, wall studs, floors, doors, cabinets, furniture, paper, pallets, musical instruments, and tools. Even in a modern house filled with wires, pipes, insulation, and machines, the frame may still depend on thousands of feet of lumber. Steel and concrete are powerful materials, and modern life depends on them. Their strength comes with a heavy industrial path. Steel usually begins with iron ore mined from the ground. In a blast furnace, iron ore is heated with coke, a carbon-rich fuel made from coal, at temperatures that can rise above 1,500 degrees Celsius. The process separates iron from oxygen in the ore and produces large amounts of carbon dioxide. Concrete has its own hidden heat. Its key ingredient is cement, often made by heating limestone and clay in a kiln to about 1,450 degrees Celsius. Limestone contains calcium carbonate. When it is heated, it releases carbon dioxide as part of the chemical change that forms cement clinker. So concrete carries emissions from both fuel and chemistry. Wood follows a different route into a building. A tree grows by using sunlight. Its leaves pull carbon dioxide from the air and turn part of that carbon into trunk, branch, and root tissue. Dry wood is often close to half carbon by weight. When that wood becomes a beam, a floor, or a table that lasts for decades, some of the carbon remains stored inside it. A wooden chair in a kitchen, an old oak desk, or a pine roof frame is still holding carbon that once drifted invisibly through the air. The value depends on how the forest is managed, how long the wood product lasts, and what happens after use. A board burned soon after cutting releases its carbon quickly. A beam kept dry inside a building may hold its carbon for a lifetime or longer. Old barns, temples, churches, and houses show how long wood can serve when water and insects are controlled. Some wooden buildings in Japan and Europe have survived for many centuries because people repaired roofs, replaced damaged parts, and kept the structure breathing. Modern wood science has also changed what trees can become. Plywood is made by peeling thin sheets of wood, called veneers, from a log. The sheets are glued in layers, with the grain direction often turned at right angles between layers. This cross-grain design makes plywood more stable than a single wide board. It resists splitting and spreads strength across the panel. Laminated veneer lumber and glulam use related ideas. Glulam, short for glued laminated timber, is made by bonding many boards together into large beams or arches. A glulam beam can be longer, deeper, and more predictable than a single tree trunk. It can curve over a gymnasium, support a roof, or form part of a bridge. Cross-laminated timber, often called CLT, goes even further. CLT panels are made from layers of boards stacked at right angles and glued into thick slabs. These panels can become walls, floors, and roofs in larger buildings. The method grew strongly in Europe during the 1990s and has spread into North America and other regions. Buildings such as Mjøstårnet in Norway, completed in 2019, showed how engineered timber could rise many stories into the air. This does not make wood a perfect material for every job. It must be protected from long-term moisture. It can burn if fire design is poor. It depends on forests that need time, space, and care. Modern building codes handle these issues with sprinklers, fire-rated assemblies, protective layers, careful engineering, and testing. Large timber members can also char on the outside during fire, forming a blackened layer that slows deeper burning for a time. That behavior can be measured and included in design. Technology has brought wood into a new stage of usefulness. Small boards can become large beams. Thin veneers can become strong panels. Managed forests can supply material, while protected old forests keep their deeper ecological value. Wood remains valuable because it begins as growth, stores carbon, can be shaped with modest energy, and carries a warmth that steel and concrete rarely share. The modern world has made wood easier to measure, engineer, and build with at scale. That deeper understanding also makes the material feel larger than human design, because natural wood requires something no factory can create from raw chemistry alone. It requires a living planet. A living planet gives wood its deepest meaning. Stone can exist almost anywhere solid worlds form. Mars has basalt plains, dust, cliffs, and ancient riverbeds carved into rock. The moon has grey regolith, which is broken stone and mineral dust, made by billions of years of impacts. Asteroids carry metals, silicates, carbon compounds, and ice. Comets can hold frozen water, carbon dioxide, methane, and dark organic-rich dust. Across space, matter can gather, freeze, melt, crack, and collide without life ever appearing. Wood belongs to a much narrower story. Natural wood needs biology. It needs living cells that can build walls, move water, and keep growing season after season. A rocky planet can have mountains without forests. A moon can have ice without roots. A star can help forge heavy elements without leaves ever opening under its light. Iron, nickel, gold, and many other metals are born through cosmic processes inside stars, supernova explosions, and collisions between dense stellar remnants. Those materials can scatter through space and become part of new planets. Wood follows a more delicate path. It requires carbon, hydrogen, and oxygen, yet those elements alone do not make a tree. Carbon has to enter a living system. Water has to stay liquid on a stable surface. An atmosphere has to hold gases in the right range. Light has to arrive steadily enough for photosynthesis. Photosynthesis is the process by which plants, algae, and some bacteria use light energy to build sugars from carbon dioxide and water. On Earth, this process helps shape the air itself. Cyanobacteria, tiny photosynthetic microbes, were releasing oxygen more than 2 billion years ago. Much later, land plants spread across damp shorelines and open ground. by about 470 million years ago, simple plant life was beginning to colonize land. By the Devonian period, more than 300 million years ago, tree-like plants were building early forests. Wood needed that long chain of steps. It needed cells that could survive drying air. It needed roots reaching into soil. It needed xylem to lift water upward. It needed lignin to stiffen cell walls. It needed fungi, minerals, weathered rock, and decaying matter to help create true soil. Soil itself is a living mixture, shaped by microbes, roots, water, air, and broken minerals. A planet with bare rock and water still may not have the kind of ground that supports forests. Even if life exists somewhere else, trees are not guaranteed. An ocean world could have life beneath ice, with no dry land where trunks could rise. A planet around a dim red dwarf star might have different light conditions, different seasons, or intense flares that change how surface life evolves. A world with simple microbes might remain alive for billions of years without ever growing forests. Even a planet with plant-like organisms could take another path, making soft mats, floating fronds, or mineral shells instead of woody trunks. Tree-shaped life may be one solution among many. Wood may be Earth's particular answer to gravity, sunlight, water, and time. That makes ordinary wooden things feel quietly astonishing. A chair leg is shaped from tissue made by a living plant. A floorboard carries carbon once drifting in the air. A pencil holds fibers arranged by growth under bark. A guitar top may come from spruce selected because its cells carry vibration with unusual clarity. A wooden spoon in a drawer may be carved from maple, cherry, beech, olive, or birch, each shaped by a tree that grew in a real climate, in real soil, under real light. Compared with ice or stone, wood is intimate. It has a species. It has grain. It has rings. It has a biological past. A piece of wood points back to rainfall, roots, leaves, fungi, sunlight, and years of slow growth. On Earth, forests can make wood seem common. Stacks of lumber sit in hardware stores. Paper fills books and boxes. Tables, doors, and houses make wood part of daily life. From a cosmic view, that familiarity becomes the surprising part. The material near the hand may be one of the clearest signs that this planet is alive in a rare and generous way. Earth can grow structure from air. It can lift water into trunks. It can turn sunlight into something strong enough to build shelter. That thought changes the feeling of any wooden object nearby. Its surface becomes a small reminder of a living world that learned, over immense time, how to make light solid. A simple wooden object can hold the whole story in a quiet form. A chair leg, a floorboard, a pencil, a spoon, or the smooth side of a table may seem small after traveling through forests, fire, ships, and deep time. Yet the same material connects all of those scales. At the smallest level, wood begins with cell walls. Those walls are built from cellulose fibers, shorter binding sugars, and lignin, the tough substance that lets plants stand tall. Those tiny walls gather into tubes, fibers, rings, trunks, branches, and whole forests. A tree lifts water from soil through xylem. It opens tiny pores in its leaves to take in carbon dioxide. Sunlight powers the chemistry that turns that invisible gas into sugar, and some of that sugar becomes wood. That one process links air, water, light, and living tissue. A board in a quiet room still carries that origin. Its carbon once drifted through the atmosphere. Its grain once followed the upward path of a tree. Its rings may carry traces of wet springs, dry summers, insect damage, crowded shade, or a fire that passed through without killing the trunk. Some wood becomes a record. Tree rings can help date ancient beams, shipwrecks, cabins, and old tools. A narrow ring can mark stress. A wider ring can mark a generous season. A scar sealed inside a trunk can preserve the memory of flame. Time in wood has a physical shape, circling around the center. The same material also became human history. Wood gave early people digging sticks, spear shafts, tool handles, shelters, bowls, canoes, fences, wheels, barrels, and roofs. A fire made from dry branches released energy gathered by leaves. Charcoal helped furnaces burn hotter, giving metalworkers the heat needed for iron. Ships made from oak, pine, fir, cedar, and teak carried people across rivers and seas. Forests became homes, villages, workshops, instruments, bridges, and moving hulls on water. Modern materials have changed the world, yet wood remains close. Steel and concrete hold towers and roads. Wood still frames houses, stores carbon in beams and furniture, warms interiors, carries sound through instruments, and forms engineered panels large enough for modern buildings. Plywood, glulam, and cross-laminated timber show how small pieces of tree can be arranged into strong new forms. The tree grows slowly. The material can serve for generations. That long service matters because dry wood can keep captured carbon locked inside a useful object for years, decades, or even centuries. In the forest, wood follows another kind of service. A fallen log becomes damp, dark, and soft. Fungi send fine threads through its cells. Beetles open tunnels. Moss holds water on its surface. Woodpeckers carve cavities in dead trunks, and other animals later use those spaces for shelter. A nurse log can hold seedlings above the wet forest floor, while it slowly returns nutrients to the soil. Wood gives support while alive, then habitat after falling. Seen from Earth, wood can feel common because forests, lumber, paper, furniture, and firewood have surrounded human life for so long. Seen from space, the material becomes more astonishing. Stone can form without life. Ice can gather far from any forest. Metals can be made by stars and scattered into new worlds. Natural wood needs photosynthesis, land plants, liquid water, soil, atmosphere, roots, fungi, weather, and long evolution. A living planet has to build it. A wooden object nearby is therefore more than a useful thing. It is stored sunlight. It is captured carbon. It is preserved growth. It is shaped life made solid enough to hold weight. The surface may be smooth beneath a hand, or marked with grain, knots, pale streaks, dark lines, and small changes in color. Those details come from a real tree that grew through real seasons. Somewhere, rain touched its leaves. Roots entered soil. Wind pressed against its trunk. New cells formed under bark in a thin living layer. The tree answered gravity by making wood. The forest answered time by making more. And humans, finding this material everywhere around them, learned to carve it, burn it, bend it, build with it, sail with it, and keep it close. Wood remains one of Earth's quiet gifts, a sign that this planet can turn air and sunlight into shelter. A gentle reminder that the ordinary things beside us may carry the deepest histories of all.